So I think we are good to start today's session. Welcome to the day 10 of your internship program with Devins Edu Growth powered by Sampin Technology Private Limited. So today's topic is generative AI and speech processing. So today we have with us Dr. Sandeepan Dhar, who is currently working as the postdoctoral researcher at the Digital Audio Processing Lab in the Electrical Engineering Department of IIT Bombay. Dr. Dhar have earned both his PhD and MTech in computer science and engineering. Hello, sorry for the network issue it was. Okay. So Dr. Dhar have earned both his PhD and MTech in computer science and engineering from the National Institute of Technology, Durgapur. His doctoral research has basically mainly focused on voice conversion using generative AI algorithm. His broad research were very much interested in exciting areas such as speaker identification, speaker verification, speech command recognition, speaker anonymization, text to speech synthesis, singing voice synthesis, multimodal image analysis. Additionally, Dr. Dhar is the co-initiator of the soft computing and machine learning groups. His work has been published in several leading international journals and conferences such as IEEE, TNNLS, and such as IEEE TAI. So we are delighted to have him here with us. Welcome, Dr. Dhar.
So hello everyone. Thanks for this brief introduction. So today I'll be giving a section for 2.5 hours on generative AI, specifically focusing on multimodal aspects. I'll start from image such that it will be more interactive for all of you. Later I give you very simple fundamental knowledge on image processing, such that we can then shift to speech processing and music processing, and how generative AI algorithms can help us in order to synthesize. Specifically, I'll be focusing on the speech generation part. So the whole talk will be on generative AI. So I'll be focusing the thing that, assuming that we have no knowledge of now on any generative AI algorithm. So I will take very fundamental examples. Specifically, I'll take the help of the mathematics in order to make you understand. So that you will get the very basics of how generative AI algorithms basically works. So let me share my screen. So if you want to see it, just do let me know. So I hope my screen is visible. It's okay.
No, sir.
Is it visible? Hello. Is my screen visible now?
No, sir.
Wait. কি বলবো মানে aku জয়েন করবার চেষ্টা করেছি কিন্তু জয়েন
Hello, sir. Am I audible?
yeah.
Sir, I think your screen is not like shared properly. Kindly, can you share your screen entirely?
That is, but the option is not coming in my but- so you cannot see anything.
No, sir. No, no. And apart from this, sir, can you use microphone? Like your voice is little bit like low.
Just give me just couple of just
Hello, sir. Manish this side. Am I audible, sir? Yeah, sir. Yeah, sir. I think you have a better sound now. You can proceed, sir.
can you see anything? Hello? How can you see?
Yes, sir. The screen is visible, but then your voice is too low to be audible, sir. It would be better if you could connect a microphone, sir.
connected to a microphone. So wait, another microphone let me use.
Yeah, sir. Now it's better, sir. It's perfect now.
Now is it perfect now?
Yeah.
Okay. So actually now it's another microphone. Okay. Anyways,
Yeah.
so meanwhile, just let me again share the slides. Let me open my slides. Okay. Again, I just restarted my system.
Sure, sir.
Let me just complete the setup. So I'm just opening a Jupyter notebook and all those. So it's already there in my tab, but I restarted, so it is gone. So it's just
Sure, sir. Take your time, sir.
yeah, it is almost ready. Uh, third. Can I remove this part? Oh, it is not
Yes,
going.
you are audible now, as well as the screen is visible.
Okay, great. Yeah. So sorry everyone for this inconvenience caused. So, anyways, so as I mentioned, so I'll be starting from very basics of it. Uh, so I hope if people have already gone through these things, means what machine learning is, what deep learning is. But still, I'm just refreshing again the very basic things, because all the things that I'll be that I have incorporated in my slide and Jupyter notebook and all. So it will be very much related with the very basics of the machine learning. Then we go to the deep learning part. So as probably you have already known that what learning basically means. So when we perform any task, when the machine is supposed to perform any task, if with experience the performance get improved, then we say that the machine is learning. And there are many aspects where we used to use in earlier cases deterministic algorithms, where we used to give the data to the model or the algorithm and used to write the whole algorithm, and based on that the whole algorithm used to give us the desired output. Yeah, so in a traditional, as I was saying, in a traditional algorithm, we give the data and we also write the program, and we get the desired output. Whereas in machine learning or AI-based algorithms, we give the data, and in a supervised mechanism, we also give the associated output, and we expect that the model will understand the basic feature from the data, and it will try to map by learning the feature how it is associated to the target output, and then it is indirectly learning the program, whether we are not giving any hard-coded program to it, whether it's trying to program by its own self, such that it can map the input data to the desired output. This is how machine learning algorithms works. And probably you have already gone through that it has supervised, unsupervised, reinforcement learning. So these are the main learning mechanisms of the machine learning algorithms. Now, the basic things about AI, deep learning, machine learning is function approximation. So, what exactly function approximation does, just as I explained, that we have some input data X and we have some output Y. So, I'm taking the example of a supervised learning mechanism. Now, this f of x is the AI algorithm. Take it as in machine learning or deep learning. Now, function approximation, because the map this is nothing but a mapping from a domain to a range. So we have the domain of input and we have the domain of output. So basically, the AI model is doing nothing but is mapping the input to the output domain.
Hello, sir. Am I audible?
Yeah.
Sorry for the interruption, but like your screen is not, can you reshare your screen, sir? It's not visible actually. Yes, it's completely fine, sir. It's visible.
It is visible
Please
now?
continue. Yes, sir. You can continue. Thank you.
Okay. So whenever it will become, I mean, you won't be able to, see the screen. Just let me know. I don't know why it is happening. So that's the reason. Means I often don't like to, use Zoom. So I mean, my system, I often face this kind of problem in Zoom. So anyways, so whenever you face this kind of issues, just let me know. So I'll reshare my screen. And don't hesitate to say. Anyways, so what I was saying is the function approximation. The function approximation is the primary
Sir,
thing.
sir, sorry to
Yeah.
interrupt, but it's showing again.
Wait.
Yes, sir. Now it's correct.
Let me figure out why it is happening. Is it okay now?
No, sir. Again, it,
So is it now visible?
no, sir. Only part of your screen is visible. The rest is covered in black screen.
It is visible now, I guess.
Yes, sir. Yes, sir. It's visible.
Yeah.
So sir, the problem exists while like sharing your screen in like the whole entire screen.
Oh, when I'm sharing the full mode, then it is becoming like that.
Yes, 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 sir.
Okay, let me share it now in this way only. Otherwise, so okay. As I was saying, that the X is basically your input domain and Y is basically your output domain. That is the desired output that you expect. Now, when you give this, when you make the model see what is the input and what is the output, the model is basically try to approximate by tuning itself the parameters, the hyperparameter associated to it. Now there's a reason any AI algorithm, machine learning, deep learning is basically called as function approximation, because it trying to approximate the basic behavior, nature, characteristics of the algorithm, because it is not a deterministic algorithm where we have hard coded the exact algorithm. Rather, it is doing some approximation such that it can try to learn the associated weights or the, as I said, the hyperparameters. So in a way, in an indirect, it is an indirect estimation of the function that's supposed to be the original function. Say, for example, that if we would have an original function, deterministic algorithm for mapping x to y correctly, then this approximation, we basically want the function to be as near as closer as to a deterministic algorithm. So that is the reason it's called function approximation. So that is what this mentioned over here. Now, how this deep learning context? So because machine learning algorithms is also does this, mapping from domain X to Y. But how it is different from deep learning? So how deep learning is basically different from this machine learning context. So in machine learning, there are many different algorithms. Like say, for example, you have this decision tree, or even if you take the regression problem. So in these algorithms, in a way, the function behavior of the function to some extent is known. We have some algorithm because let's say for example, linear equation y equal to mx plus c. We do not, say for example, try to approximate the exact value of m and c, but we at least know if it is a linear equation, definitely that is the characteristic y equal to mx plus c, and or maybe if there will be multiple gradient, that m1 x1 plus c1 plus, or maybe m1 x1 m plus m2 x2. Say for example, there are multiple inputs, so this variable associated to the input, that is x1 or x2 x3, that is m1 m2, all these things may be unknown. Maybe in a way, when the model will try to learn that, it will learn the exact values of m1 or m2 or m3, but at least the behavior, the characteristics of the function is known, because it is a linear equation. There may be non-linear regression function, but in non-linear regression also, we at least know that what is the characteristics of it. But how deep learning is different, because in deep learning we do not have any idea about how the function is basically the model trying to approximate the function in a way that it has no idea about any given function. Like as I mentioned, in linear regression or non-linear regression, we at least have the basic behavior characteristics of the algorithm. I mean the equation. Only the variables associated to it is unknown. Whereas in deep learning, we do not provide any specific equation or characteristic. We expect the model itself learn. And this is how it is different. And the most primary difference is in machine learning algorithm, we extract the features and then the model gives us the desired output. Whereas in deep learning, we directly give the input and model try to understand all probable features from it, extract all probable features from it, and then give us the desired output. So this is the machine learning and deep learning, the difference between it. And I hope you have already gone through it. But as because I'll be jumping to the generative AI, so I thought that I should cover it again, such that it will be easy for us to discuss later on. Now, okay, just let me know, Miss, you have gone through the CNN parts and all. Convolution neural network you have gone through?
No, sir.
Okay. So as I already mentioned that in deep learning, given the input, we don't need to extract any specific feature from the input. Rather, we directly fed the input to the model. Model, in a way, using different filters, try to extract all probable feature and try to map the input to the corresponding output. And during the learning process, it updates all the associated weights and also the bias values such that it becomes the optimal way, it gets the optimal weights or bias associated to it, and it can, in the inference stage, it can map any input to the output. And convolution neural network, it helps in getting those relevant features using different filters from the input data. So say for example, this is your input. So given the input, the model, the convolution neural network model will use different filters. So initially it will try to extract the age level informations from the input, then some object level information, and the final part layers of it, or the filter has the last layer of the convolution, basically try to extract the overall abstract information of the input, exact input it was being fed. So now using different filters, it has an abstract representation in the lower dimensional space of this higher dimension data. So what is a higher dimension? Higher dimension means the, say for example, you're using an HD image. So the number of rows and number of columns, if you convert it into matrix, maybe it will be 1024 into 1024, means 2 to the power 10 into 2 to the power 10. This many number of rows and columns may be present in very huge high dimensional images. Now, to work with such images is very problematic because it has so many pixels associated with the image. You know, in order to compress the image in a way that we can get the most appropriate information associated with the original image in a lower dimension. Lower dimension means the dimension will be reduced, but we should not reduce in a way that we are losing some meaningful information from the input data. So convolution neural network basically helps us in order to extract the most meaningful information from the input using different filters. So this is the difference between deep learning algorithm and machine learning. If it would be a machine learning algorithm, you must have to write the pre-processing code for it such that you get the features and then you feed it to the this classification model. Whereas in deep learning, you are not doing it because you already have these filters that will be extracting all the probable features for you, and then you have the neural network model to do the classification. Means given the input data, which class it belongs. Say for example, the input is a car, so it should definitely belong to the output class car. And this is the basic difference between neural network and deep convolution neural networks. So it's not, the right hand side is not basically deep convolution neural network, it's just deep neural network. So the left hand side, it has one input layer, one output layer, and just in between there's a one hidden layer. So this is the initial neural networks with which the AI, the whole area, the domain of AI was being emerging maybe 50, 60, 70 years or so. So we may think this AI has emerged just recently, but the idea of perceptron, this is called perceptron learning, was invented in 1955, 56 around. So this is called multi-layer perceptron. So instead of one hidden layer, you have in the right hand side image multiple hidden layers. That is helping to get more evident information, more significant information on the input. Whereas if you use some filters, as I mentioned in this particular slide, if you add some filters before it, then you'll get some meaningful information. Then you can use this part, this is a multi-layer perceptron, in order to do the classification. So it is basically mapping the input data into the corresponding label, this is the output. But if you add the convolution, then it will definitely extract out all the related meaningful information from the input data, and then it can do. Otherwise, if you directly using multi-layer perceptron, you have to again do the pre-processing. Now, say for example, this is one example what I actually try to mean. So if the convolution layers, so convolution layers is basically trying to find out the the age level information in using different filters. And in the last layer, it will having the most important features of the related to the ages, and it will feed it to say for example this deep neural network in the end, and then it will map the features that embedding is also called the embedding. It is also called the embedding space or latent space, or sometimes it's called the flattening factor. So basically, in abstract information, nothing else. So this abstract information gets mapped to the corresponding output by the neural network, and only the convolution is done by the different filters. So that's why it's called convolutional neural network. Convolution means feature extraction. The neural network does the classification only, and then comes the generative AI models, and is very important. So my main focus will be on generative models. So now I have just opened my Jupyter notebooks. I hope it is visible.
Yes, sir.
Yeah. So before I proceed, just let me know regarding AI ML, how far you have learned, means such that it will be easy for me to make you understand these things. Means related to the AI ML, how far you have learned, means what are that already been covered. The last things which you have studied.
Sir, supervised learning, unsupervised learning.
Okay. So convolution you have not studied. I mean, as of now, you have not gone through.
No, sir.
Okay. Oh, anyways, so I have just given you one brief idea about how convolution works. So now, we'll go to this generative AI part, and this will be very mathematical. So you do not need to have very high level idea of mathematics, of engineering mathematics. This is just basics. 10 plus 2 related math, probability, statistics, lineage, all these things will be going through. Mainly probability and some calculus, and very basics. It means not very high level. So we all are familiar with the Bayes theorem. So this is called a conditional probability. So you can think that this X is basically nothing but your input, and Y is the output. Now, output in a classification model definitely nothing but levels. Say for example, you have given an input data which has images of male gender and female gender, and Y thus have two levels, male or female. So we can think like, instead of having string as level, male and female, we can convert it to numerical values. Let's say for example, male means 1, female means 0, or vice versa. So when you will be feeding X, that is an image, to the model is supposed to map it to the corresponding Y, that is either 0 or 1. So using Bayes theorem, we can understand this conditional probability is nothing but probability of X given Y, probability of Y divided by probability of X. So what is the probability of X? The probability of X is basically the input data. And when the whole data set is given to you, then you can have the access of what is probability of X given Y. That means a table will be given to you, say for example, X and Y. So you are expected to learn what probability of Y given X, but you also have the information of what is the probability of X given Y, and what is the probability of Y and probability of X. So what is the probability of Y? If you have a lot of images of male and female gender, and you have the corresponding level, so you can simply find what for a particular Y equal to 0, what is the probability? Means total number of samples and number of occurrence of Y equal to 0, means say for example 0 belongs to male gender. So how many times it has appeared among all the samples? So say for example the number is the number of time male gender has appeared is, say for example, K, and total sample is say for example capital N. So k by n, the simple probability. The probability of y basically means there should be some level associated. The probability of y equal to 0. So for the probability of y equal to 0 means male is what? K by n. So if k is the number of male, then definitely capital N minus of k will be number of females. So number of females, capital N minus of k divided by capital N will be the probability of y equal to 1. Simple. So if you have an access of the data set where x and y both are present, then you can simply find out what is the probability of y. Similarly, you can also find probability of x. So probability of x will be the summation of probability of y given x into probability of y equal to 0, that is main, and then plus again probability of y given x, x given y into probability of y equal to 0. So this will give you the total probability of x. X means the input data. So in a way, you also have this information and also this information. So given the table, you will get all this information. Only after you compute this, then you can get the probability of y given x. So y could be either 0 or 1. So once you will have all this information, given a new data of x, you can simply map it to the corresponding y. So using Bayes theorem, we can simply, we can understand the working mechanism of classification algorithm. But the classification algorithm, all classification algorithms do not extract this condition and probability to give you the class belongingness. It is an idea how the model basically works using Bayes theorem. But the CNN or other supervised algorithm you have studied so far, maybe say for example decision tree or other Bayesian boosting based algorithms. So not all algorithms learn using this conditional probability. Machine learning algorithm definitely learn, but I'm saying that not all algorithms supposed to learn using Bayes theorem. But using Bayes theorem, we can get a very clear idea about what basically classification means. Classification basically means nothing but learning this conditional probability. What is the probability of a class belongingness of a given data X? That is what the conditional probability is. Now, if you learn this thing very well, now say for example, here you have two data points, distribution data. So one is yellow color dot points, one is a red color dot point. So if you can very easily say, given a new X, maybe say for example, it belongs to, its color is yellow, and you can very easily map that Y is equal to yellow, given the input data X. That basically means you have learned the probability so well that you have also learned indirectly a decision boundary into between these two distribution. What decision boundary tells us? So decision boundary helps us in understanding that given a new, how the training data. So now you have the training data. So how one single line or a curve. So in this decision boundary, it may be linear or non-linear. It may be a curve. It may be a straight line. So using a straight line or maybe a curve, a non-linear decision boundary, how we can well distinguish two classes. If there would be multiple, then multiple, but at least in this case, we are dealing with binary class, yellow balls and red balls. So if we can see, a model is basically giving us the correct output, at least 9 Yeah, I don't know why it is happening. The internet, probably the internet connection is also slow. It is down here. So, anyways, so you have learned, I mean, you have understood now what decision boundary I'm trying to mean. Hello, hello.
Yeah.
Yeah, so if you have any doubt in between, just let me know. So not necessarily you have to understand every single part of it, but at least if you can get I mean, overview of these things, then it will be very easy for you in see. I mean, in these tutorial classes, you are expected to get a very overview of the algorithms. So such a way that in future, probably you are in second year or third year. So if in future you do work on this AI ML things, or maybe you join any company in industry, so this become very easy for you to at least understand, given a problem, whether you should apply consider it as supervised or you should consider it as unsupervised, when classification models are required, when these generative models are required, and how this model basically works. So every model's way of working is different, but if I mean, in a context of this learning mechanism you want to understand, then you can find that there are many similarity within this learning mechanism, like supervised, unsupervised, reinforcement. So that's why my basic focus here to give you not exactly how each and every algorithm works, but how, say for example, supervised algorithms work, how the generative algorithm works, such that if in future if you learn any new generative algorithm or any new this classification algorithm, then it will be very easy for understanding actually what you are trying to do. So if you are using any classification model, basically you are trying to indirectly find this decision boundaries. So I mean, if you can perfectly estimate the best optimal decision boundary, your classification accuracy will be very high. That your model can very easily understand, given a new data, which class it should belong. Okay, so as of now, it's say for example, it's I mean, after training, the model has learned this decision boundary. Now, given a new data, it can very easily map that given data whether it should belongs to this right hand side yellow class or this left hand side red class. So if it can correctly do it, then definitely it will give you very high accuracy. So in training any AI algorithm, you basically have this training, validation, testing, and then once the whole model, I mean, you get the very high training and validation accuracy and also very high testing accuracy, then your model is deployable. So you can do some inference. So if the inference also giving you the very expected output, then definitely this model is deployable. Now comes the generative AI models. So generative AI model is very much interesting. See, so far we are actually trying to learn the decision boundary, which can distinguish between these two classes. Now generative models not only learns the distribution of two classes, means how it can be distinguishable, but also learns the distribution of it. The dotted line that I have covered is basically indicating that it is not learning a decision boundary. Rather, it is definitely learning how these two data sets, training sets are basically, or the classes are basically distinguishable. But in a way, you're also learning the distribution of this class, red and yellow. Now, how this thing helps? See, earlier case in discriminative model, it is only learning a line, or I mean polynomial or linear, which making these two classes distinguishable. But if you can also learn that how that points are being distributed within them, then you can sample new data out of it, and then you can generate basically new data. So if we can learn indirectly that how this this red color balls or yellow color dots are distributed, then learning these features, we can sample new synthetic dots which looks like maybe I mean y equal to red, or maybe y equal to yellow. So when we talk about generative AI model, basically we are dealing with this joint probability. So if you again recall what you have studied in your class 10 plus 2 probability, so what joint probability is? Joint probability is probability of occurring two events at the same time. So for example, X is a specific image and Y is correspond means associated level. As I said, red color ball or yellow color ball. The probability of occurring the two events that X and Y is X is, say for example, this particular any ball from this and its corresponding level is red. The probability of occurring these two events at the same time, if you can learn, it basically you can also learn, you are also learning indirectly this classification. How? Because probability of joint probability of X and Y is nothing but probability of X given Y into probability of Y. In your again, and if you write probability of Y comma X, then it will be nothing but probability of Y given X into probability of X. Now see, probability of X comma Y, joint probability, we are also finding this conditional probability of Y given X into P of X. This part, isn't it? That means using generality model, we can definitely do classification, but we will indirectly be learning the distribution. So that is the most advantage of any generative AI algorithm. Now, let me go to one example. So this is a Gaussian naive-based algorithm. See how it is working. So I'm taking the libraries only, I mean the sklearn libraries. So it will be easy for you then. So first, say for example, I'm generating some samples, 300 number of samples of having this number of feature 2. Then I'm calling this Gaussian naive-based algorithms. I'll tell you that how this Gaussian naive-based algorithm. So it basically does follows this the joint probability estimation only. Then I'm feeding the X. This is a training sample and the associated weights to it. Then I'm giving new X to it such that it can predict the corresponding Y. Then I'm also using a discriminating model, logistic regression. So have you gone through this logistic regression?
Yes, sir.
Okay, then it will be easy for you to understand. So logistic regression is a classification algorithm. Then I'll show you means how this things works. So this is the, I mean now I'm taking the means every samples and then plotting you the decision boundaries of Gaussian naive-bayes and logistic regression. So logistic regression is a classification algorithm. So if you remember, it forms a S-like curve. For linear regression, you get a straight line. For logistic regression, you get what? A S-line curve which passes through this y-axis. So if you remember, then if you make y equal to 0.5, so any value coming above it will fall into class 1 and any value coming below it will fall into class 0. But see, logistic regression is basically doing nothing but a normal kind of normalization. So equal to if you remember the function is 1 by 1 plus e to the minus of x. So it is taking the x in doing the normalization, then it is giving you the corresponding label. So you have to just condition that if it above the threshold, then it belongs to class 1, and if it below the threshold, then class belongs to 0. But you are not doing any Bayes, you are not applying Bayes theorem directly into it, but indirectly it is doing this thing on probability of y given x. So if your logistic regression has learned the feature distribution so well, then it perfectly can map given a new data to its corresponding level. That means it is nothing but learning a very well decision boundary. So now see this line. So as of now, this line looks very linear. It may be non-linear as well, maybe a curve as well. So see this logistic regression, what is it doing? So it has learned the data distribution so well that these 2 points, distribution of points, red and blue, are very well distinguishable except a few points. The blue has appear over here and some 2 red points are appear over here. But it is learning accuracy is almost 0.99, 99% accuracy. So it is learning the decision boundary and it is giving the accuracy of 0.99. Now see this Gaussian name-based model. So accuracy is slightly less, 0.98. But anyways, our objective is here to understand how this works. Now see here, it has formed just a decision boundary. But in this case, it has formed one kind of curved line, which indirectly gives us an estimation how this data that belongs to blue point will actually scattered and how these red points are scattered. That means indirectly you are learning this y equal to x, but also the probability of x. So once we learn this probability of x means the data, say for example, x over here means indicating the blue color balls, dots, and here it is indicating these red color balls or dots. So you are again learning the probability of x and probability of y. You're not only learning how it has been classified, but you're also learning indirectly these 2 things. That means if you learn this p of x and p of y, then you can also synthesize. Synthesis means generate new samples which can fall in this particular region. That means it has similar type of distribution as its training samples. So this is the advantage of generative AI models. So that's why if you remember all the generative AI algorithms so far you maybe heard or maybe you're using, taking ChatGPT as an example. So this large language models, so this is nothing but generative AI models. So they learns the distribution of when you train the model, using different type of data. So maybe if you're training in a large language model, definitely you need a textual transcript. So I'm not talking about the type of the data, whether the text, image, video, speech, or any signal. Rather, I'm telling you the working mechanism. If you use any language model as well, or any other generative model for image, or maybe for speech, or maybe for music, whatever you use, indirectly it is doing nothing but learning the distribution of the data. So once it can learn the distribution so well, then it can generate new text, new images, new videos, and new speech, or even music. So I hope this example has given you an idea about how classification model you are already been familiar with. So since a long time you are using this classification model. The biometric system is nothing but a classification. The face recognition system, speech recognition system, the fingerprint detection system, all are classification. But in this last few years, we have found a very this area of generative AI suddenly got a boost after the introduction of different algorithms, specifically GAN, attention mechanism, and these BART models. So these have revolutionized the field. However, the generative AI models are previously it was also there. The Boltzmann machine, Mark models, these are nothing but generative models. Anyways, the basic objective I hope you have understood. So you have any doubt regarding that, or if you want to say that whether you understood or not, these 2 things means the basic difference between classification and generative model, discriminatory generative model. I hope it is clear.
Yes, sir.
Hello. Hello.
Yes, sir.
Yes, sir.
Yeah. Okay. Anyways, I will be sharing this Jupyter notebook to you. Now let's try to understand this generative adversarial network model variational autoencoder model, and more specifically the diffusion model. So I'll be not giving you any insight of this BART models because it will be covered probably in the natural language processing talk. So I'll be giving you mainly the insight of GAN, VAE, and diffusion, the on aspect of image, means the common computer vision, and speech, signal and speech. Now, how this GAN model works. So I hope you have you heard this name, Generative Adversarial Network Model, previously?
No, sir.
Yeah.
No, sir.
Okay. So how many of you have used this Face app in 2018-19? In Facebook, it was very much popular by that time. So have you used that Face app in Facebook in 2018, 19, 20 this time? Anyone? Yeah. Hello. Have you used the Face app before in Facebook?
No, sir.
Okay, so I do not probably by that time you're in your school, so your parents are not allowed you because if you are in second year now, probably you're in class 8, 9, or 10 probably. So anyway, so there was a Face app, so it is also available now. So it was supposed to, convert your image into an given prompt into different images. Say, for example, you want your image to be converted into a very old people face. So it can easily can convert. It can also convert you into a very childlike face. It can also be converted into a different gender. So it has different kind of specification. So it has been trained with one specific model called Face GAN. So it is like a conditional GAN model. So I will tell you what conditional GAN model basically works, how works. I guess Ghiblification definitely you have used. Don't say that Ghiblification you have not used.
Yes, sir.
Yeah. So can anyone explain me what Ghiblification basically does? Don't hesitate. Just such that I want this to be very interactive.
Sir, I think it is used for making those Ghibli arts that we saw on the internet. I'm not sure though.
Yeah. So basically that means it has some sort of artistic, understanding of some, specific type of artistic understanding. And when you give an image to it, any source image as an input to it, it try to transfer the style of the image similar to that of the artistic this means stroke with which it is familiar. So I remember in 2020, I guess, yeah, in 2020. So this GAN models and generative AI models was just been started. I mean, so there's just people has just started using these models by that time. It was very popular in the, among the fraternity of, AI. Earlier, people mostly used to work on classification. So in 2020, teachers, I remember still that our lab mates, gifted one a picture of our professor, our supervisor. So it was the image was a real image. So we transferred the style of the image in such a way that it looks like the starry nights of this Van Gogh image. The Van Gogh strokes, if you go through an internet, so there is some uh, turbulence type of strokes you can find. So after converting those images, training those images, those image data set of Van Gogh, we found and we could easily transfer any data to Van Gogh like strokes, and we gifted that to our supervisor in 2020 Teachers Day. Now giblification, see how, I mean, people have, I mean, it was in trend for last many months. I too tried, I guess all of you have gone, I mean, tried it to see how a given image of yours looks like after giblification. So it is nothing but called style transfer task. So what style transfer does, given an image, it don't actually change the content of the image. Rather, it transferred the distribution of the content, the feature associated to it. So when do giblification, your content, say for example, your face was there, it only get converted into, a table or any other object. It will be remain same, your face only. But your structure, the style will get changed. So it's nothing but a style transfer technique, and GAN widely been used for this specific task. Before that, variational autoencoder was popular. So I should have included VAE first, then GAN. So anyways, so VAE was initially popular for this generation of images, synthetic images. Then GAN came into existence in 2014. So almost 10 years back, and it has revolutionized the field of generative AI. Then diffusion now in trend. So how VAE is to work. So say for example, X is your input, and there is an encoder. So what is an encoder? So as the name indicates, so it encodes it. It encodes the data to what? To a latent representation. What is latent representation? It is an abstract representation. As I just mentioned, the convolutional neural network converts the higher dimensional data into lower dimensional space, extracting the most significant information from the input data to a lower dimensional, intermediate representation like Z. So encoder Q, this phi, is basically the associated weights. Try to map the X into Z. So that is the, you can indirectly, you can relate it to the probability of Z given X. So you try to get the optimal Z that has the most meaningful information of X. Then comes the decoder. So as the name decoder indicates, it try to decode it to some other domain. So what domain? So here I have shown the same reconstruction. Means it has converted X to a domain Z, lower dimensional space, and Z to again X. That means it has reconstructed. But what if you would have a target domain Y? That is your X is your image, your own image, and Y is your maybe target images which looks like this, have the Ghibli arts. So if you can use the decoder to convert your data into Ghibli images. But say for example, the reconstructed images, say for example, not that good as Ghibli arts, then you can find the difference, the way we find error. So you can find the difference between the reconstructed Ghibli-fied art and the original Ghibli style images. Then you can fit the loss, or the error basically nothing but the loss. In machine learning deep learning we call it loss. Loss you can feed it to the decoder and encoder, such that encoder decoder can learn how much how far this generated image is similar to the or dissimilar to the Ghiblified art, such that you can tune its parameter phi and theta, such that given new once you do train it, even when you give a new X, the reconstructed image should looks more similar to Ghiblified art. So this is how variation autoencoder works. However, this is basically not VAE, it is basically autoencoder. So in VAE, we have this mean and variance, but I just wanted to make it very similar. So it is basically VAE, not, only variational encoder. So sorry, it is only autoencoder. So in variational autoencoder, we again find the mean and standard deviation, and then we try to condition the decoder. So anyways, so this is the basic idea of autoencoders. Now GAN, how it is different? See, in GAN, you also have X, this is the input data, but the learning mechanism is totally different. How? Let me explain. Now, one advantage of GAN I will tell you later. So now see, you have a latent representation initially, whereas in autoencoder, you are getting the latent representation in the intermediate space given X. Now, say for example, you have a noisy, total noisy data, and you are giving it to the generator. The generator will construct some meaningful data out of it. But what kind of data should produce or generate? That we should specify that it should look like X, because X is our target domain. So generator will take some random noisy image, then it will generate some images in the intermediate space, which looks like target data X, but there is a supervisor. This is called discriminator. What discriminator does? It is like a supervisor who is supervising whether the image that you have generated and the actual image whether looks similar or not. If if it maps the generated image into a class of 0, then it will say that no, your generated image still looks far differ from the original image. And if 1, then it will think that your generated image is so closely matched with the original image that it is unable to distinguish and directly get to the 1. However, there is something called Nash equilibrium state where it cannot say whether the image belongs to 0 or 1. So it gives a probability of 0.5 and call it a Nash equilibrium state. This is how the GAN model works. And then comes diffusion models. So I will go brief into GAN. So I have the codes and everything. I'll tell you the very basics of it. Then you have diffusion models. Diffusion models. So diffusion model, how it works? It learns in a chain using a chain probability. So you have the input. So first it will add some noise into it. You'll get the X1. Then again you add some noise into it. Then you get X2, and so on. You'll get a complete noise image from the actual image, and again you will try to reconstruct using the chain probability. And then there is a decoder, basically a neural network model, which learns this amount of noise with denoise. I have to denoise because you have not added noise in the forward pass. In the backward pass, you have to understand how much noise is being added, so you have to denoise. Then it reconstructs. So it's a so one thing probably you have gone through that in every cases. I have just taken the example of X and X hat or X dash. But actually, if your domain input and output is totally different, then you can take instead, you can relate it like instead of X dash, it will be Y. Okay. So maybe from one domain, you completely in another domain you are mapping. So if you again try to understand the thing that autoencoder maps input data to a latent static, which is called discriminator. It keeps on finding whether the generator one is similar to the original or not. And based on the value or score, you can unlearn whether the generator is near to similar or not. Then in diffusion, use chain probability. Hello? Hello? Because internet still. Hello?
Yes, sir.
Yeah. So in diffusion, use chain probability to do the same task. Now let me go to this example. I'll explain the code. So is a diffusion code. I'm directly going to the GAN code. Okay. So this is what I actually try to mean. So you have this some noisy image. There's a generator who try to draw some image which it wants to match like the Mona Lisa image, and the detective, there is a discriminator which is critic, it will every time take the image painted by the generator, and it will also take the real image of Mona Lisa and keeps on finding whether it is similar or not. So these are just abstract idea of what GAN works. Now let me go to this. So I'll explain the code. So let me go to some samples. Now see this. So this is the initial samples generated by the generator, means like the painter. So initially it is generating very noisy like image. It seems like that it has not learned the target domain. What is the target domain? It's a target domain is the MNIST digit data, numerical digit. Now this is step 500. It's called iteration. So after 1000 and so on, it is improving but the improvement is very less. But gradually it is improving. Now see, after around 3000 iteration, you can see some values appearing. Then 4000, it is more clear. Then 6000, far more clear. Now see, in 8500, much more clear. And so on, if you keep on going, so probably yeah. So this is the output you should get. So if you keeps on going, after some very long iteration, you'll get very clear images. So you started from this part, now you obtain this part. So there are many things, means loss function. We also have the optimal cost, transportation cost, etc., etc. There are many nomenclature. So it is very high level things. So inside mechanism mathematics is very high level. But if you just want to know the basic idea of it, this is how it works. You start from very noisy images, then in every iteration try to improve, and ultimately you'll get a very clean data. But this learning is very unstable. Okay, so let me go to the code part again. Yeah. So just here you can see I have just generated some noise, random noise in TensorFlow. Then this is creating a 28 cross 28 image and reshaping it to one-dimensional space. Then you have shown the images that just like this one. Then I'm going to the generator. See, so this is the generator function. So it is just, just to make you understand, just two layers I have taken. So it will take 256 as an input, then 784 to is So it will give you this 7684 as the output. Then you have the discriminator. So discriminator will again, discriminator is nothing but a CNN model, classification model. So generator, see how generator discriminator the architecture is different. So generator basically is more similar to this autoencoder because it takes an decoder of the autoencoder. It takes an latent random noise in lower dimensional space and generate a high dimensional data. So the generator is more like a decoder, isn't it, of autoencoder. It's a reverse of the convolution. So actually convolution what does? It takes a high dimensional data and map it to a lower dimensional space. The transpose it is also a transpose of the convolution or reverse convolution or deconvolution. Then the best nomenclature is deconvolution. So using deconvolution, you basically take the latent representation and we can generate the corresponding output. So decoder is more similar to the generator. Now let me go to this. Sorry, this part. So this is the function you have just created. This very small, multi-layer subdomain neural network. So this is this percent loss. I will also explain that. Then the optimizer. Then here the gradient calculation basically starts. So I do not know whether you are familiar with the gradient descent algorithm, optimizer, all these things. Are you familiar with these things?
No, sir.
No, sir.
Yeah, so that's why I'm not going much deeper into it. Let me go to how, I mean, just to let me explain you this binary dynamic cross and tree part, so that you can understand this. And I don't think this mathematics that I explained to you is very complicated, isn't it? It's very easy. Now see loss function. See, as of now, we have just gone through the learning mechanism, how GAN was, VAE works, or diffusion works. But there are many components associated to it, like architecture or the building blocks of it, like this encoder decoder. In a similar manner, loss function is extremely important, and the optimization algorithm. Loss function and optimization algorithm is one of the most primary important part of this AI algorithm, generative AI algorithms. Okay. In machine learning, you don't exactly have this loss function because many machine learning algorithms don't have parameter learning concept. So it don't have exactly the, some parameter that it has to learn during training. So it follows some probability, the base theorem only, and based on that it gain like information gain in decision tree. So based on probability only it find the decision, the highest gain, and based on that it takes the different nodes and sub nodes and get the final output. Then you have the support function vector machine. There also you learn the weight, but it is not like, you have a loss function, it keeps on tuning the associated weight. It just take you to higher, higher dimensional space and try to find the decision boundary which is a plane, which can make the two classes or multiple classes, linearly distinguishable. So machine learning algorithms exactly don't have this optimization. Optimization, then learn loss and optimization associated to it. Mostly it is associated to deep learning algorithms, and I already explained what deep learning is. Now, say for example, as I just mentioned, probability of y given x. Now, say for example, given a data x, the probability of class belonging is y is p of hat. If x belongs to the class y equal to 1. So say for example, only two classes are there, 1 and 0. If it belongs to class 1, then it is p of hat. Otherwise, it's 1 minus of p of hat. And simply means using Bernoulli distribution. So I guess the Bernoulli expression also you have learned in your class 10 plus 2 or in engineering mathematics. So you just take the power of the class. So p hat of y 1 minus of p f 1 minus of y. Now if y is belong to 1, is simply put the value and you get p of hat. Why? When probability of y given x, when y equal to 1, then you get p of hat. Otherwise, you'll get 1 minus of p. And if you take the log out of it, then you get this equation. Okay. Now see, this is a handwritten note. So if you search with my name, Sandipan, the medium blog, you'll get all these informations. I've written it down over here. Which books to study to go, deeper into the AI, machine learning, deep learning, all these things I have just mentioned over here. So these books are not required for you because it is for masters or PhD scholars. You can go through this book. Okay, it's very much important because because you are undergraduate student, and if you are applying for any data science related job, then this particular approaching almost all machine learning programming, the Abhishek Thakur. So this book is, I mean, at least 2-3 years back, till then it was very famous. So people who used to work on industry, they used to follow it too much. So this Abhishek Thakur was grandmaster and Kaggle grandmaster for 3 years, three consecutive years. So you can follow this book. I do not know whether now any better book is available, but I used to go through this. I mean, it is only for the implementation. You don't get the very deeper understanding, but this book is very much helpful. It is hardly around 1,000 rupees. So, anyways, so here you will get many things associated to the speech synthesis and deep learning, which tutorial to follow. Now, say for example, if you go to this visualization of speech data, here we get the codes as well as I hope the materials are associated, materials are available. So I explain everything. Yeah. Not in this though. Yeah, see, if you want to go deeper into the speech processing, then what book you should go through, or everything I have written down. Okay. The different videos related to speech and GAN, etc., etc. Everything I have just everything you get over here. All probable channels are I have linked. Okay. So just search with my name. So from there only I am showing you this particular slide. So actually this part is very much essential. If you want to understand how GAN works, there is something called mean max algorithm. So there is a loss function. So there is between generator and discriminator and mean max algorithm keeps on working. So how this mean max algorithm works? What is my slide? Okay, yeah. Yeah. So this is a detective, is a discriminator. It keeps on trying to minimize its error of indirectly mapping the synthesized image as real. Are you getting? Means the objective of the detective is to every time say that generator has unable to draw the image exactly like Mona Lisa. This is his ultimate objective of the detective, the discriminator. So it keeps on trying to minimize this error, whereas this generator keeps on trying to maximize its accuracy of replicating the real like image of Mona Lisa, such that for detective it become very indistinguishable. So when at a particular moment of time the generated image will become very similar to that of the real data, then we say that no, detective has unable to find the point, means unable to detect the difference between these two. Now it is saying that the probability of belongingness of the generated data belongs to 0.5, means it is unable to say whether it should belongs to 0 or 1. So it says simply a probability of 0.5. So now let me go to the diffusion part. So that was I was saying that the training of GAN is very unstable. So as because you have not gone through the loss function as such, so I'll not make you understand means what is how we can interpret this particular plot. Okay. So as because it is very new to all of you, so let's skip this part because you want to understand now. Yeah. So see, there are different type of distribution called unimodal and multimodal. So what is unimodal distribution? In your class 10 +2, you have studied that you have studied histogram, I believe. So in histogram, what we used to do? So in the x-axis, we used to take the ranges of some data present in our given test case, and frequency. There is a number of data present in particular category or range, and then we can find plot this histogram. So if there is only one peak, this kind of histogram is called unimodal distribution. But if there are multiple peaks like that, okay, then we call this multimodal distribution, multiple peaks. So now, if you try to draw the distribution of amino acid digit data, which is numbers from starting from 0 to 9, you will get multiple peaks. So each peak basically indicates the distribution of the particular numerical number present in your data set. Okay. So if this kind of distribution, means multimodal distribution, is present in your data set, then it becomes very difficult for the GAN model to replicate the exact distribution. Because if it is unimodal, only one type of data distribution is there, then it is very easy. If only Mona Lisa image is there, then it becomes very easy. More easy for the generator to draw it. Rather, if I provide multiple images to it and to draw each of the image correctly, then it becomes very difficult to generate. That's the reason why multi-model scenarios are much more difficult than unimodal scenarios. So see, if multimodal distributions is present in your data, then most of the cases your GAN model makes lot of problems in the synthetic data. So it's unable to generate very well replicated data in after generation. So this is kind of an example. See, there are multiple type of animals were there in a training set. Multiple type of celebrities were there in an image set. So that's why when it generates the image, then it is so distorted. Just looking at it, you can find the distortion. So when multimodal distribution are there, then often it is very difficult for the GAN model. But there are many ways to deal with this. So I'm not going too much. There's a divergence theory, so I'll not go much deeper into it. It will become very difficult otherwise for you to understand. Then comes the diffusion. So diffusion, as I mentioned, that you have the input data, say for example S. Every step you are basically adding some noise into it, and you're getting some complete noise. Again, you are trying to reconstruct the S in the reverse process. So in the forward process, it is basically trying to get what will be the x of t given the x of t minus 1. I hope you can understand the thing using the okay. Let me. So it seems like it will be difficult for you to understand. Possible, I'll take some other example to make you understand. But it's very important because I'll share the code, and codes are available in GitHub as well. You can make multiple repos, but if you don't understand the things, but it will no meaning. Okay. Now see, this is your input data x naught, and then you are adding some noise, say for example Gaussian noise to it. Say for example Gaussian noise is represented with this kind of n, and as because every time you are changing the mean and deviation, so I'm just representing the noises with different numbers. So you add some noise n1 to it, the image in the input data, and you get x1. Again, you add some n2 noise to it, and you will get x of 2. Now see, what you are actually doing, you are trying to map x of t, the future state, from the past state, x of t minus 1, isn't it? And this type of chain is called hidden Markov chain, HMM. Sorry, hidden Markov chain, CHAIN. So what hidden Markov chain says that if you are in current position t, then you can minus 1, t minus 1. So if your current position of t, then from tth state you can predict t plus 1, exact t plus 1. And if your current position of is t, then definitely you have appear from just the last, say t minus 1. That means t minus 1 to t and t to t plus 1 is, interrelatable. So using hidden Markov chain, we can find out the just 1 plus 1 future state. So in diffusion, we basically try to add noise and get the just t plus next the t plus 1 this noisy representation of the input. And in the reverse diffusion, we do exactly the difference, means we try to denoise it. So after denoising, we tried that the denoise data should look some other distribution. Here I have just reconstructed the same input, but usually the objective of the diffusion is to get some other distribution. So I'm not going to very details about it. So let's see. This is the some input images. So after some certain iteration, the generated images are like that. So initially the reconstructed images just doesn't look very nice. It is morely noisy. But after certain iteration, high number of iteration, it will start looking like it is appearing in the correct way. Now let's try to understand very basics of signal processing thing. So such that we can directly jump to the speech processing. So do you have any idea about this signals, time domain, discrete domain, or not?
No, sir.
Okay.
No, sir.
Yeah. So say for example, is a sinusoidal signal. So this is I'm again taking the help of this 10 plus 2 thing, means signal. It's very basics of the sinusoidal signals. Say for example, you have some sinusoidal signal. Now is a time domain. Why? I'm sorry, it's a continuous domain. Why continuous domain? And it is also time domain. Time domain means it is changing. Value is getting changing with that respect to time. The amplitude is getting changed up every time instant. Now continuous means between any 2 points there should be infinite number of points present. But when you do discretization of it, you actually take some selected points in the intermediate space. So if you have a line, continuous line, there in any 2 points, there will be infinite number of points. But if you discretize it, if you say that I will sample it in every, say for example, some second, then within some second we get single points. Okay, we'll call discretization. So it is converting a time into some discrete, giving some discrete representation of the continuous time signal. So we have different devices for this, for analog to digital converter, which does this. Then there is something called frequency. What is frequency? Number of cycle per unit time. Okay. So if frequency is very high, that basically means this number of cycles within a particular unit of time is very high. Okay, so let me take so here I have taken one example. Like see this. This is the equation of any time domain signal. So yt, so I have represented xt. So anyways, so xt is a sine 2 pi ft. What is 2 pi? And f is the frequency. So if you multiply with 2 pi, so it is basically becoming the angular frequency, because it is sine of 2 this omega t. So omega is nothing but 2 pi f. So and phi is the phase difference. Okay. So if you used very high number of frequency, then we'll get more cycles within some interval of time, and your frequency become higher and higher. So let's take an example. I'm making the frequency very low, like 15. Okay. Now see the frequency values that appeared in 15. Okay. Now let's try to hear the sound. Can you hear anything?
No, sir.
Yeah, you should not. Because our auditory system, human auditory system, can hear sound if and only if it ranges from 20 hertz to 20 kilohertz. It is 15 hertz. You definitely cannot hear it. But let me take some higher value of frequency. Maybe 25. I guess very, very high bass you can hear. Let me take more higher number. 35. Still not audible. Let me more higher number like 55. Oh. Okay. Yes. Yeah. Can you hear the sound?
So it's not clear.
Definitely it's not clear because the frequencies as I explained that, so it should be from 20 hertz to 20 kilohertz. But if a higher frequency, if it is a higher frequency, then only you can hear the sound more properly. So I've taken 100, I guess 55 as a frequency or what, 45 or what I have taken. No, sorry, 50, 155. So 155 is very less. So you should not hear it very properly. But anyways, you can find the appearance of the sound, the high bass it has. Now, let me show you some other experiments with signals. Now, say for example, if your signal has only, like this. Yeah. Say for example, you have only one frequency. What is the frequency? 440. 440 hertz. Then ideally you should get only one single point. What if you add another frequency to it? Now it's like sine 2 pi 450 t plus sine 2 pi 660 t. There are two signals now getting added. Then you should ideally get two frequencies. So what I am doing, I'm doing a Fourier transformation, or it is called frequency domain transformation. So in the amplitude domain, in the time domain, you cannot see exactly, it is very easily, you cannot visualize. However, see, if one signal is there, it's a very highly sinusoidal because one signal is there. If two signals is there, you can see, this patterns, regular patterns are coming, but it is not interpretable as it is. Sorry. So here two frequencies are present. So if you do the frequency domain transformation, Fourier transformation, then you will get this two frequency. When you add more frequencies, like here I have added three signals, different frequencies, 440, 670, and 880. Then you see there are two lower frequency, 440 and 660, and you will get a higher frequency, 880 over here. Okay, so let me again play this sound. So the 450 is, I guess, audible, isn't it? Hello? Can you
Sir,
hear?
can you play again?
Yeah. Is it audible now?
No, sir.
No, sir.
So I guess I have to Add sound as oh share sound. Yeah. Sorry. Let me see. It's not going. Yeah. Share sound. It should go now. Yeah. I guess it is audible now.
No, sir.
No, sir.
I have added the sound, desktop, share sound, studio high fidelity. Is it audible now? Is it audible
No,
now?
sir.
Still no, sir.
Hmm. I could record this cloud on screen now. Select this option if you want others to hear sounds coming from your computer. Yeah, so that is what I've done. So organizer, can you ensure what kind of problem actually because of which I cannot share the sound? Because isn't it the option I should mark? Means I've marked this share sound option.
So maybe the sound is too low to listen, I
No,
guess.
it's not that low. Means
So are you able to listen?
completely.
We are not able to listen.
440 Hz is the high frequency sound. Okay, let me play some other sound, then you can ensure.
Subject going to the country.
Can we hear it now?
Yes, sir. Yes, sir.
Yes, sir.
Oh, then probably this 440 Hz you cannot hear, but I can hear it completely. So, anyways, so maybe because of this reason. So, anyways, what I wanted to make sure, wanted to tell you that if you see if you add the different signals put together, you will get different frequencies. Now, our human speech has multiple frequencies associated. So just looking at the audio data, you cannot make distinguish over which are the frequencies are there. So that's the reason we have to do, for frequency domain transformation, the Fourier transformation. So I'm not explaining exactly what Fourier transformation is because it will be again take much time to explain. So rather I will explain you certain other things. So see, for example, this is another time domain signal. It has been associated multiple frequencies. Frequency 4, at least there are some frequencies are there. Then 1, 2, 3. So this spikes basically tells you the exact in values of these frequencies. Okay. Now, if you do this spectrogram analysis, so spectrogram is an analysis where you can get the frequency. See, in time domain, you get the time and amplitude only. When you do frequency domain transformation, you get the frequency and the presence of the frequency. How much? What is the presence of the frequency? Not only the which frequency it is, also the presence is the magnitude associated to it. So you get in frequency domain the magnitude as well as the frequency, the exact frequency as well as the corresponding magnitude. So you can see this frequency is very much prominent, okay, as compared to this one. Now, if you do spectrogram analysis, then you'll get this some lines. It's called formants. So formants also an indication of the content. I mean, it's basically an indication of the content associated to any speech. So here you don't have any content, so it's it is very straight. You get a very straight point line. So this is also called harmonics. So let me play this now. I hope you can hear the sound now. Yeah. You heard the
No,
sound?
sir.
No,
No.
sir. No, sir.
Good. Maybe the low frequencies are not actually capturing by the Zoom. I mean, this is not a problem of my device. It is problem most probably Zoom is unable to capture low frequencies. So let me play the human speech. Now you see, as I was saying, that when you hear the human speech, in time domain, it is very complicated to see how many signals, I mean, frequencies with which it is being comprised of. But then when you do this Fourier transformation, you'll get different spikes. So there are multiple frequencies with which the human speech is comprised of. So if you, I will let me play.
Subject learning to the conscious.
And you can hear this sound at least, because this it has very high frequency regions.
Yes, sir.
Now this is a spectrogram. As I was saying, that in spectrogram you get the time as well as the frequency associated to every I mean every time what is the frequency associated to it, and also the magnitude. Okay. Now see, when you get the time domain signal, you only get the time and amplitude value. So it's basically indication of the loudness as well as how loud the speech was. Then if you do frequency domain transformation, you get the presence of the most prominent frequencies in the Fourier domain, frequency domain. Then when you do this obtain a spectral, I mean do the spectrogram, then you get time versus frequency, and the values is called the format. So for this format, it should give you an indication of the content of the speech. It is a male spectrogram. So let's understand that it's a very filtering of this spectrogram, and this is called pitch. So pitch is also, I mean, pitch basically indicates how what was the most prominent frequency at a particular instant of time. So there come, as I mentioned, there are multiple harmonies usually present, but most prominent frequency present at a particular instant is called pitch, and this is called prosody, or melody associated to any speech or singing data or music data. Now let us consider I've done some pitch shift. So the pitch was very high. I shifted the pitch quite low and loud. Now hear it.
Subject learning to the conscious.
Now I have shifted the pitch more. Yeah. Now this time I have higher the pitch. So if you make the pitch of a child, so it's a child voice. So if you make the pitch very high, it seems like very female-like sound. If you make the pitch very low, it it seems like very male-like voice. So male vocal tract has very low pitch, but loudness is more. Whereas for female, the pitch is very high. Now let me show you this, how this vocal tract actually looks like. Yeah. Like see this one. So this is the vocal cord. So when you do take breathing, so it gets opens. Otherwise, it always the fold is always closed. So when we try to say something, from our lungs, airflow passes through it. Okay, passes through it means this vocal cord. So make vibration over here. So based on this vibration, we have this nasal cavity and oral cavity. So what is nasal cavity and oral cavity? Let me explain. So this part is called nasal cavity and this is called oral cavity. So when any vibration, I mean, your vocal, see, when we utter anything, so in that phase, our vocal cord vibration takes place. So this vocal cord this cord vibration when is and the air passes through this oral and nasal cavity based on this place of articulation and manner of articulation. Place of articulation is where which part of the vocal cord, I mean the vocal tract, the is oral cavity, nasal cavity, which part of the nasal cavity and oral cavity is taking participate in the speech production system. Based on that, different phones are being generated. Say for example, I am saying O I E A. So just try to say O A E A. Then try to say no in neo. So in neo, your nasal cavity is very much too much associated in making the sound neo. But when you're saying A, A, E, A, so the vowel sounds. So there you can I mean, just touching your vocal cord, you can find that, the vibration. You can just feel the vibration. O, A, E, A. So this vowel sound or the consonant sounds, I mean, just touching your vocal cord, you can understand how the vibration is taking place. And mostly this oral cavity is taking participate. Whereas for these sounds, as is so no, this in those sounds, this nasal cavity as so this is the place of articulation or manner of articulation based on the different phones. Phones means basic building blocks of any sound. Like this Sharavarna is Vyanjan Varna. So Sharavarna and Vyanjan Varna is the basic building block of Assamese or Bengali or any Sanskrit, any language derived from Sanskrit. So we have Sharavarna or we have Vyanjan Varna. Then combining this Sharavarna and Vyanjan Varna, we form different words. So if you break the words, you again get the phones. So the basic sound is called phones. Okay. So using different phones, any word is comprised of. And these phones are been, I mean, you can find, I mean, if you get the understanding of what phones, like say for example, I'm just uttering my name, Shandipan. So when I sing Shaw, O, so it has a sound sh and has a sound sh, this in this sound actually the air is coming out of my teeth, but my teeth is closed. So the phonetic sound for this sound and is different. So just if you break the sound in phone level, then you can well understand what is the exact words phones with which the word is comprised of. So phone this is called phonemization. So this phonemization from this phonetic context, you can also trace which part of your vocal trace was associated when generating this sound. So if I'll play the sound, so then very easily you can find out that which part of my mouth was basically associated in making the sound. When I say so you can also understand which part of my vocal tract was associated. So that's the reason sometimes you do phonemization to understand the words more properly and the speech more properly. So I'm not going very deeper into it. I hope you will get some idea. So now I will tell you something related to my recent works that we are doing in our lab. Then I was also, I mean, after my PhD submission, I also work as a research intern in Sony Research India. So there also I work on text-to-speech synthesis. We have worked with this different data set of Sony Entertainment, specifically for dubbing purpose. Then in my PhD, I worked on this voice conversion, vocal style transfer. So I'll show you some samples. So I hope it will help you understand. So in music data also, I'm as of now working in my postdoctoral research. So let me show you some samples and I'll make you understand what exactly we are trying to do. Yeah, so this is one recent work we have done from our lab. So I'll show you what the model is specifically trying to do. So we have a diffusion model. We have just made one diffusion model. So it takes the music score. So in music score, you actually have the lyrical content of a particular music singing data. So the lyrical content, from the lyrical content, you get the text, extracting some embeddings, and then we are training the decoder such that given the text and the phone of the lyrical content, it can generate the corresponding image spectrogram because we already have the audio data. So we try to minimize the loss between the constructor and the original one. And then in the inference stage, we want to get the best optimal audio. So as of now, we have worked on this Arijit Singh's singing versus. So our lab is the first in India, first Indian lab singing TTS, or it's also for singing word synthesis. So the input is basically your lyrical content and also give the pitch information. The output you get the corresponding audio data in of the singer, of the vocalist. So these are the original data we have considered. So in the input, you must have to give this content in Hindi. So you have trained only for Hindi and only for one male voice, the Arijit Singh voice. Then you have to do the phonemization. So I have already mentioned you the how to do the phonemization of the text. You'll get more, utterance level information. Then notes. Notes means, in music we use different notations to represent different notes. C sharp, D sharp, like that. So we have to convert into that notations. Then note duration. That means till how long this note was present in the song. Then phone duration. Phone duration means to how long one particular phone was present. Then there is something called slur. Slur basically means any variation of the pitch within sentence within the self. So it is not. It's not that much relative. So these things I hope you had understood. This phone, lyrics, note, and duration of the note, and phone duration of the phone. Now see, we have generated some samples. So let me play the. See, these are the baselines, and baseline is already available models, and these are proposed one. Yeah. Let me play something. So it's a ground truth. Okay, the original data. So we expect that once the model is trained with all original data, is supposed to be given any audio and trained without data. Then we found these samples. So you can hear the sound is breaking. So it's not that quality is not that good. There is another baseline module. Here you can also find the distortion. Now let me play our one. So as you can see that this sample is far better than these two models. So let me play another sample. So the baseline model sounds is very, it is words. But let me play our own. So this is the, I mean, as you can see, it's a better than this two, but still you can hear some background noise. It is because of when we downloaded the samples and we did some source separation, because background music was there, so we separated the background noise from the audio. So because of that, some distortion already actually present in the original data also. So that replicated in our generated samples. Like let me play it again. So you can see the here the echoing sound of the from the background. So the thing was like in Hindi Bollywood data, we although have lot of data available, but for research is very less. So you cannot download and use any data for your research purpose. You have to take permission before that. So there is a one of the limitation of the working in Hindi singing data, and we are trying to produce the first Indian Hindi singing data for as an open resource data so that everyone can use. Let me play some sound of TTS work that I did during my work in Sony. So this is one diffusion-based architecture that we built. So let me play the sounds. So demo page. Probably the demo page link is not visible. Oh, wait. So I updated the link. So this is the ground truth. Why is not playing? So it is not taking down some time to load it.
In Fort Worth, there occurred a breach of discipline by some members of the Secret Service who were officially.
So this is a ground truth. Now this is
In Fort Worth, there occurred a breach of discipline by some members of the Secret Service who were officially traveling with the president.
Now see this sample.
The 9, the eggs, I keep. 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 The 9, the.
So these are all generated samples, but you see how natural this sound seems like, as if some nature. I mean, it is a like human-like voice, but it's totally, generated speech. So you train the sample such that we get a very natural-like sound. Okay. Then let me show you what exactly voice conversion is. So in voice conversion, we basically do this kind of generation. So my slide is visible.
Yes, sir.
Yeah. So one voice conversion also kind of a this speech generation task. So where what we actually do is we do not change the content of the input. Say for example, the input speak of the input speech is a speaker is a main speaker and uttering this content hello in his accent. Now the target speaker, say for example, a female speaker, and the content is Shuharam, and she is uttering in her native accent. Now the model will learn both the vocal text of the source and target, and it will convert in such a way that it seems like that this target speaker is uttering hello. So this is the basic thing of what basic concept of voice conversion. So you do not change the content of the input, you just make the target speaker sounds like that of the input speaker. I'm sorry, so it sounds like that the target speaker is uttering the what the input source speaker, or you can say like input speaker is uttered. So there are many types of voice conversion. One is called singing voice conversion, where we get the singing of one source speaker and you just convert it to the target speaker vocal texture, such that it seems like that the song is basically sung by the target speaker. Okay, so I'm not going too much into this thing. So some research papers we have published and have generated now. Yeah, so let me show you some samples of one of our recent work. Now this. These are the original sound samples.
Captain Nemo stood up. Here and there she saw maps and pictures hung upon them. And over this great domain Buck ruled.
But as you can see, these are generated samples.
Here and there she saw maps and pictures hung upon pegs. Oh dear, I shall be too late. And to wonder what was going to happen next. But that if he assured us on his word as a gentleman that we were trespassing.
And then let me hear some new verse.
Tall, black rosewood bookcases. He escorted Molly and Alice, the judge's daughters, on long twilight or early morning rambles. Stood back from the road.
Okay, so did you find that? How natural these samples are as compared to the original?
Yes, sir.
Yeah. So let me tell you some new research is going on in the field of speech synthesis, but it's not speech synthesis. It's from brain. People are working on now on brain-computer interfaces. Even the fraternity of speech synthesis. So they are trying to decode the brain signal into textual transcript, and then from TTS. They're using the TTS model to decode it and generate the corresponding samples. We can hear, like, say for example this one. So we are not working on that. I'm just playing one video. It's also available on YouTube.
Or Anne and Bill to have a conversation through our brain decoding.
So it is the University of California, San Francisco. The researchers are working on brain signals.
An actual real life application of knowledge. Right. They create a demonstration where we're decoding the text, the speech, and the avatar.
You are wonderful.
In the training lab, we really focus on restoring voice to people that have lost it due to conditions like stroke or ALS? What we're picking up on are neural activity related directly to the attempts to move her facial muscles.
Now you will
and
find that
that's what we're
the lady is thinking something. She is unable to speak, but the model is decoding it and
Okay.
generating the avatar. See.
giving them the ability to communicate again with their loved ones.
Sir, we can see.
Looking to do. I was thinking about running to the store.
What time will you be home?
In about an hour.
Do not make me laugh.
See. So this is now the fraternity of the speech synthesis working on brain signals decoding. So it was earlier voice conversion. People also work on text to speech synthesis, and then singing voice synthesis. Then speaker anonymation means you just anonymize the vocal identity with some random speaker. And then now the recent trend is this brain computer interface of building brain computer interface for generating the corresponding speech. So regarding till whatever I just mentioned, do you have any doubt? You can ask me if you have. So yeah, you can ask me anytime, if you have any doubt. Or if you can now, if you have any doubt, you can ask me. Or if anyone want to say anything related to means what so far you have understood or anything else that was it interactive? Did you learn anything else? Or means anything new?
Sir,
I know.
what was the difference between GAN and VAE? Like I
Yeah.
couldn't understand properly.
So yeah, see, GAN has an additional discriminator. It's totally independent. It's not attached to the generator. Generator generates, discriminator is totally different. Say for example, two different people. So one is generating, one is discriminating. Whereas VAE is a total end-to-end system. It does not have an independent system. So the encoder and decoder put together is this autoencoder. Whereas in GAN, generator is totally different. So you can assume generator is like an autoencoder. And discriminator is totally working independently. So generator is generating, discriminator is distinguishing whether generator samples similar to the original one or not. Whereas here, in case of autoencoder itself is taking care of its, errors made by its own self. That is the basic difference.
Okay, sir.
Anything else?
No, sir.
Okay. So, this TTS, singing voice synthesis, or voice conversion, have you before Ganthro, or means are you aware of these things, or? Because mostly I have seen that people are aware of this ChatGPT related generative AI. But the speech synthesis or singing voice synthesis, still people are not much aware of. And definitely there are many applications, apps available, softwares available, but still there are many researchers taking place because the softwares I see here, there are things, I forgot the name of this application. Suno AI, I guess. So where the Suno AI can given any textual transcript, it can, given any lyrical content, it generate the corresponding song. But these songs are very, biased towards this Western Western music because it isn't trained with Western music. But Indian classical is very complicated. Indian type of music, in form of music. So this adaptation of different type of singing style, different type of this gharanas is very much complicated. So now people are working on that. So there are many other complications. It seems like that we have already have this generative AI model, so it is already everything is done, but it's not like there are many problem statement, very concrete problem statement people are trying to work. We all are working. in a way to somehow contribute something to, make the things better. So, so you, most of you belongs to Assam?
Yes, sir.
So I also studied in from Jorad Engineering College. I did my graduation from there. So after a long period of time, I'm interacting with the students from Assam. So usually in talks, most of the talks where I have communicated with different institutes. So it is not from Northeast. So this is for the first time, though I am from Assam, but since a long time I'm staying outside. So after a long time, I got some opportunity to interact with the students from Northeast India, from Assam, from my own place. And yeah, I hope this, whatever I said, is not a very, I mean, I could not go very deep because you are second year students, probably. So definitely you don't have very deep understanding of that. But in abstract understanding, I hope you have found from my talk, and at least what is the research is taking place in the field of generative AI, specifically on the field of speech. And these signal processing aspects, these things are, I mean, you have to, you have to go through these things if you want to understand. But I hope I could make some, basic understanding of these things. And all my, so if you search with my name, Median blog, my GitHub repo, or many things you can get. And I used to have a YouTube channel as well, but only few videos related to this voice conversion is available there. But mostly you can find my Medium logs, and my codes are also available. I hope these things will help you to understand. And anyways, I will share this Jupyter notebook. Okay. So anyone from Jorad Engineering College? No, I guess. So most of you are from which institute?
Sir, all of us
Royal.
from Royal Global University.
Huh?
All of us are from Royal Global University.
Most of you are from Royal Global University.
Yes,
No,
sir.
sir, all of us.
All of
Oh,
us.
okay, okay, great. Okay, thanks. So I am finishing my talk over here. Okay.
Okay, sir. Thank you.
Okay. Thank you.
Thank you, sir.